Hello, welcome back. We are going to today get into light calculations using these two equations to solve for things like wavelength, frequency, energy. So we have these two equations, C equals lambda V, or lambda nu sometimes, where C is the speed of light, lambda is the wavelength, and V is frequency. Then we also have E equals hv, which E is energy, H is Planck's constant, and then V is frequency again. So with these two equations, you can kind of go back and forth between wavelength and frequency. You can also add energy into the equation of a wave. So when we're talking about this, the speed of light, we're talking about the electromagnetic spectrum, which all of those waves are traveling at the speed of light. And so the speed of light is 3 times 10 to the 8th meters per second, or 3 times 10 to the 17th nanometers per second, depending on what your unit for wavelength is. And then your Planck's constant is 6.63 times 10 to the minus 34th. So let's go ahead and try an example question. Let's say I have a wave, has a wavelength of 450 nanometers. We're assuming this is a wave of light. What is its frequency? Okay. So if I'm given wavelength, I'm solving for frequency. That means I'm going to use this equation. And if I rearrange it to solve for frequency, so V equals C over lambda. Okay. So speed of light, and since my wavelength is in nanometers, I'm going to use the 3 times 10 to the 17th nanometers per second over 450 nanometers. And I'll plug that into my calculator. So I get I'll do 3E17 divided by 450. Gets me 6.7, let's call it 6.7 times 10 to the 14th. So 6.7 times 10 to the 14th. And for your unit, the nanometers cancel, so it's just per second. Or sometimes that's hertz. Okay. So that's how you would do that one. Now if I wanted to know the energy of this, because sometimes it might say, what is the frequency, what is the energy, okay? Then I would take this number, since I have the frequency now, I'm going to plug it into that equation. So the energy for this would be Planck's constant times my frequency. So I'm going to do 6.63 EE negative 34 times 6.7 times 10 to the 14th. And that energy is 4.4 times 10 to the negative 19th joules. So that's actually a way where you can use both equations. If you're given wavelength and trying to solve for energy, you have to go through frequency. You have to solve for frequency first. Or if you're given energy trying to find wavelength, again, you'd have to go the other way, or do the same kind of thing. All right, so let's do one more with frequency. So a wave of blue light has a wavelength of 550 nanometers. What is its frequency? Oh wait, this is another. Oh, well, we'll do this one too, and then we'll do one more. So this is another one similar to what we did up there. So frequency equals C over lambda, 3 times 10 to the 17th over 550, speed of light over your wavelength. So we get 317 divided by 550. That gives me 5.5 times 10 to the 14th per second. Okay. All right, let's do one with frequency. What is the wavelength of a wave that has a frequency of 9.8 times 10 to the 15th hertz? Okay. So now we're solving for frequency, so it's going to be, or we're solving for wavelength. So wavelength equals speed of light over frequency. So it's a very similar, no matter what you're solving for, it's going to be speed of light using that equation, speed of light over what your given is. So so speed of light, 3 times 10, we'll use the 8th, we'll use meters per second here, over 9.8 times 10 to the 15th. So 3E8 divided by 9.8 EE15. And that gets me, I'm going to put that in scientific notation, a really tiny number. So let's call it 3.1 times 10 to the negative 8th meters. And we could have probably put that in, nanometers, but we'll just keep it in meters. All right. I hope this helps. Let me know if you have any questions.